Hello, beautiful people. Today I just thought we'd do something a little bit different from what we normally do of trying to build something or put something together. And I thought we'd have a talk about some of the most fundamental and kind of basic ways a computer or any digital technology communicates, how they actually send information. Whether it be when we press a button, do we turn a light on, or something more advanced like, how do we actually communicate inside a computer what the temperature is outside. Uh, Before we get onto that, though, let's take a quick look at what we're going to be learning today and what our success criteria are. So, what I'd like you to walk out of here with is an understanding that digital technologies use a math system called binary to communicate. We should probably say a number system rather than a math system, but here we are. And success criteria. So, if you have done these things when you walk out today, you have been successful. The things you need to do to be successful today is you need to write your birthday in binary and write and decode a message in binary. Now, if you don't know what binary is, that's cool. That's what we're here to learn. Now, one little note. I am doing this live. No editing, no cutting. So if I get lost or anything to that, please just be patient and please just be listening to your teacher. So I'd like to start us off so it's not just me talking the whole time with a question. And that question is, how do we measure information? And you might be going, but Mr. Fay, we don't measure information. Mate, information doesn't take up space. And you'd be right. Like, information doesn't necessarily take up space. The thing that it's stored on takes up space. But have a think about your phone. If you take too many photos, eventually your phone fills up. So it's a quantity. It's a thing that we can count and measure. So how do we measure information? And to answer that question, we need a good way to start is to ask, what is the smallest piece of information we could have? Now, this is a question that was asked by scientists for a very long time, and I'd like you to try and answer it because you're lucky. You're on the other side of that discovery and that thinking. So you might already know. You might not just have the words for it. Have a think about that. And to make that question a little bit easier, here's how I think about that question. And that is, what is the smallest number of choices you could have in a decision? All right, so if I have a decision, what's the smallest number of choices? I'll give you another hint. If you've ever played 20 questions, that might help you out. I'm just going to give you 30 seconds. Teacher, if you feel like pausing this video so they have a bit more time, that's perfectly fine as well. This is a really important question for what we're doing today. Okay, so if nobody got it, that's cool because this is legitimately a tricky thing. But I hope you have some suggestions and I hope your teacher had something to discuss with you there. The answer is the smallest piece of information we can have is something called a binary choice. Now, I absolutely did not expect anyone to say binary choice, but you might have said something like yes or no, right? Because that's two choices. If I have less than two choices, I don't really have a choice, do I? If my choice is between milk or no milk in my coffee, and my butler says, well, sir, we're very sorry, but we actually don't have any milk, then I no longer have a choice. So the smallest decision, the smallest piece of information we could have is a piece of information that has two potential outcomes. And a way of thinking about this is, let's say we have a proud dad over here who is waiting for the birth of his new child. All right? And he's waiting behind a sheet of glass, so he can't hear our doctor over here, who is looking absolutely like a Chad, right? Our doctor has communicated with our dad beforehand, and he's said, if it's a boy, I will hold up a blue card. If it's a girl, I will hold up a pink card. Now, setting aside any kind of edge cases there, let's just pretend for a moment that the baby can only be a boy or a girl in this case. This is the amount of information that is being passed through the glass by these cards is binary. It can only be one of two states. It can't be more than one of two choices. So this is a binary choice, a binary decision. And binary is how computers communicate. Now, in terms of actual technology, in terms of like what's going on inside a computer, what we're worried about is not whether or not the baby's a girl or a boy. What we're interested in is electricity flowing or not? So I want you to think of a pipe. We've got a pipe here. And halfway down, we've got a sensor. Let's make that sensor a little more reasonable. There we go. We're going to need a little thing up here. Cool. So this is a pipe or a wire, and electricity can flow through this wire. Now, for our purposes, it doesn't matter how much electricity is flowing. We are just concerned about whether or not it is there. In the real world, we do need to know how much is there, but that's for another time. Right now, is there electricity flowing through the pipe or not? And through the wire. And I want you to understand that within the little Arduino you are using for this class inside your phone, even some fridges, washing machines, there are millions, if not billions, of these little gates here, these little sensors. So, if there is no electricity flowing, our little sensor puts out a 0. If there is electricity flowing, it puts out a 1. Now, I'm just going to repeat myself there because I have a feeling I stuffed that up. If there is no electricity flowing, if nothing's gone through the pipe, our little sensor spits out a 0. And if there is, he spits out a 1. Now that 1 or 0, that binary choice, is the very definition of a digital technology. A digital technology works using binary decisions. The alternative is an analog technology. I don't want to talk about those just yet because that can make things a little more confusing. Just understand for now that a digital technology works based on whether or not there is electricity flowing or not. And I don't mean like it's switched on or it's switched off. I mean it communicates using whether or not electricity is flowing or not. Okay, so you might be going, cool, so we can make, like, we can detect a 1 or a 0. I'm just going to make that a little bit bigger for you wonderful people. 1 second. We can detect a 1 or a 0. How the heck do we use that for information, right? Because how would we even use that for numbers, let alone anything else? Because in our math system, we have lots of digits, right? We have 0, 1, 2, 3, 4. Whoop, that's a wonky 3. 3, 4, 5, 6, 7, 8, 9. We have all these digits. So we've got a lot more symbols we can use for information right there. How do we do it with just 1 and 0? And to answer that, let's take a look at how we use our 10 digits, sorry. I think it's that one. Yeah, cool. So, in our system, what we do is we take our 10 digits, 0 through 9, and we put them in different buckets. You know these, you've been taught them, they're called place value, right? And even if you don't know them as place value, you kind of get them just through fiddling with numbers. So let's say I put a 5 in here. We know that that's 1, 2, 3, 4, 5. That's 5, right? But once I go past having 9 in here, if I've got 9 and I add 1, then suddenly we do this little magic trick where we put a 1, the same symbol, into the tens column, and then we put a 0 there to make 10. So if it's in this bucket here, it is actually worth 10 times more than if it's in this bucket over here. And you'd be familiar with that, hopefully, if you've been paying attention in math, right? Each of these jumps is 10 times by 10. There are 10 tens in 100. There are 10 hundreds in 1,000. And some of you are sitting in there going, oh my God, why are we doing maths right now? Well, I'm here to tell you, most digital technologies, when you send a Snapchat to your mate after school talking about how boring Mr. Fay is, you're using digital technologies. You're using a whole bunch of math, right, just to send that one picture. But how does that work in binary, right? Binary only has the 1 and the 0. So how does that work? Well, rather than each bucket being 10 more, our buckets in binary are double the previous one. Just let me get that up for you. There we go. Right? A little bit different. So just for now, let's not worry about these guys here. Okay? We're going to have 1, 2, 3, 4, 5 buckets to put our binary digits in. And I want you to remember, this is the part which throws people. I can only have a 1 or a 0 in each of these buckets. So let's say I wanted to write the number, I don't know, the number 4. Right? I wanted to count 4, but I can only use 1 and 0. Let's have a look at that. I need to put a 0 in every place I'm using. So let's try that. 0, 0, 0, 0. Okay, that's good. And I can put a 1 in the 4's place because I have a 4. We don't have a 16. Let me get a laser pointer. We don't have a 16. We don't have an 8. We have a 4. We don't have a 2. We don't have a 1. So in binary, 4 can be represented as 0, 0, 1, 0, 0. Now, those amongst you who are still paying attention, boys just listening, if the sub-teacher could let me know if that worked, that'd be awesome. So let's say we're working with a different number. Those of you who have been paying attention will kind of notice, hey, these are all even, right? Like 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. So there's only one number here that's odd. And even then it's prime. It's 1. Okay, sick. So how then do we do odd numbers if I can only select these numbers? These are all even except for 1. Well, we've got 1. So let's say I wanted to represent, I don't know, 7. Right? I want to represent 7. Well, we can add these numbers together to make our 7. So, is there a 16 and a 7? No. Is there an 8 and a 7? No, obviously. We could use a 4, so let's put a 1 there just for now and find out. We're not using 16, we're not using 8. 4. Yes, cool, fantastic. Are we using a 2? Yes, absolutely. And then I just need a 1 because 4 plus 2 is 6 plus 1 is 7. Hooray! So my 7 could be written as, in binary, 0, 0, 1, 1, 1. Sick. All right. Now, just a little aside for a second, just to get you thinking. Focusing back up here for a second. We call these small pieces of information, our 1s and 0s, a bit. Okay, so up here I have 1, 2, 3, 4, 5 bits of information. 5 yes or no choices. The next kind of chunk we can do is called a byte. You might have heard this before. Oh my goodness. Sorry, my computer's not very happy with me. There we go, a byte. And a byte is 8 bits. So 8 0, or 1 options, which we normally split into 4 groups just to make writing it easier. It's not a thing the computer does necessarily, that's just for us. So if 8 bits is a byte, what do you reckon, this is a fun little joke I guess, what do you reckon just 4 bits is? I mean, just 4 of these 0 or 1 decisions. I can give you 20, 30 seconds just to give your teacher some answers. What is smaller than a byte, but bigger than a bit? Teacher, please feel free to pause this so I don't have 30 seconds of dead air, because I'm about to give the answer. Cool. If you guessed a nibble, you're absolutely correct. 4 bits is a nibble, 1 bit is a bit, 4 bits is a nibble, 8 bits is a byte. And when you check your phone, you might see, oh, this photo of me hitting the griddy is 4 MB, 4 megabytes. 1 megabyte is 1 million of these little guys. It's actually slightly different. It's like 1,000,024, but for now, it is 1 million of these. So if you've got a 4 megabyte photo, you have a 4 million bits, 4 million yes or no decisions that make up that photo. It's a lot of yes or no decisions to send a photo of you hitting the griddy. All right, back to work just a second. And I realized I misspelled nibble. No, I didn't. That's fine. Okay, cool. So let's just do another couple of these so we're not confused for the activity, because I am about to let you do some writing, I promise. I know I've been talking for a while. Okay. Let's say I wanted to write the number 15. Can you get rid of all this junk up here so we got a nice clean state? I would like the class to try and figure out, of these numbers up here, which ones should I be adding together to make 15? And I'm going to give you 10 seconds, if we could pause the video, and then I'll answer. Okay, let's see. 15. I could add... Ooh, that's a tricky one. I could add 1 and 4 together. Oh, sorry, 8 and 4 together. That would give me 12, wouldn't it? And then I could add 1 and 3 together, and that would give me 3. Let's do that with something that's not going to disappear. 8 and 4, 12. 2 and 1, 3. If I add these together, I get 15. So, if I wanted to write that in binary, it would be nothing in the 16th place, yes and 8, yes a 4, yes a 2, and yes a 1. So in our little system here, using only these 5 bits, we would have 0, 1, 1, 1, 1 is 15. Okay, so what I'm going to do is I'm going to finally let you do something yourselves. Thank you so much for being patient. And we're going to take a look at how we would write our birthday in binary. So I've done my own birthday here. Can we just make sure, I'm just going to give the teacher a second to pause. Can we please make sure everyone has this wonderful sheet in front of them? Okay. So all this stuff up here is stuff I've already told you about. Feel free to read it. All right. There's one more word you'll need, and that is decimal. And decimal is the system we use. Okay. Binary is the system I'm teaching you. Decimal is the system we use. All right. So what we're going to do is we are going to write our birthdays. So Mr. Fay's birthday is the 5th of August. I'll just do that one more time. The 5th of August, 05, 08. And I'm in 1990. I've chosen to cut the 19 off because otherwise this gets a bit too much. So we've just got 90 down here. So what I want you to do is write your birthday down here. I'm going to do mine again just to show you. So this is what you would do, but with your birthday. 05, August is the 8th month. I need to have a 0 in front of it because even if I don't, the computer still expects something to be there. We have to tell it it's a 0. 90, because I was born in 1990. I know, I'm old, I'm ancient, I'm decaying. Now, if you've got a lot of zeros in your birthday, you are extremely lucky. Because for that, all we need to do is write in 0. I'm going to try this. It's probably going to be a bit fiddly on my screen. Right? Easy. 0. Any zeros can just be represented by all zeros because I don't have a 1, I don't have a 2, I don't have a 4, I don't have an 8, no 16. I don't have any of them. I've got 0. So I suggest you do that first. That looks a bit like a 1, doesn't it, Mr. Fay? Now we need to go over to these ones and figure these ones out. Well, of these 5 numbers here, what could I use to make a 5? Should be fairly obvious, right? 1 and 4 is 5. You guys aren't in preschool. So 0, 0, 1, 0, 1. 0, 0, 1, 0, 1. 8. Well, very easy. I have an 8. Even numbers are super simple. 0, 1, 0, 0, 0. 9's a little more tricky, but again, I can just use 2 of my numbers. I can add my 1 and my 8 together. 0, 1, 0, 0, 1. And I've written my birthday in binary. I would like you to do that now. Now, to the classroom teacher, I'm going to give it 10 seconds and I'm going to keep talking because otherwise we have 5 or 6 minutes of dead air. Pause me, please, and I will move on to the next bit. Okay, I hope you wonderful people have done that. What we are going to do now is we've been looking at numbers. How do we send messages? When you send a text message, that's a digital technology, right? When you message your mate on Discord, hop on, I'm locking in. That's digital technology. That's using letters, so how do we write letters? I'm going to put this problem up for you. I want you to have a little think, okay? How do we use this system to write messages? How do we use this system to write messages? And by messages, I mean like using our own alphabet in English. How would we do that? Once again, my wonderful teacher friend, 10 seconds here, however long you need with the wonderful people. Okay, so what we do is we basically assign each letter a number, right? Because so long as I can keep on adding more bits, I can keep on having bigger and bigger numbers. And in fact, with every bit I add, I double the amount of numbers I can have. So what somebody much more intelligent than me did was they put together a system where each number, each decimal number that we make out of ones and zeros, has a letter associated with that. And so, for instance, this is not the case, but for instance, I might have the binary 00000001, and that might be A, and then 00000010, which is 2, because you got to remember that's our 2, that's our 1. 1 second there. Might be B. Now, that's not the case. It's a little more complicated than that. But that's basically how it works, right? So your next step is you are going to write a message to your mate. And can I really highly recommend you make it a school appropriate message, because I have had some people who thought that if they wrote a message that was inappropriate, no one would be able to tell except their mates, but you end up decoding it. So this sheet here, what I want you to do is do not write your message here. Write it on a bit of scrap paper. You can only use, at most, 32 characters. So that's 32 letters or numbers. At most. My suggestion, keep it shorter than that. Hi B, I'm bored. With an exclamation point is enough. Right? What I'm going to do is I'm going to write a really quick message down here. Okay? Hi class. Now, one thing to note, there's a space here, right? That's actually a character. Like the computer needs to know to put a space there. So that space actually has a binary number, a decimal number, a number just in general attached to it, right? For now, we're going to ignore that because our brains can do the work of putting the spaces in once we recognize the words. Don't worry about spaces, is what I'm saying. So let's take a look at this. I've got a capital H. Hopefully your teacher has a set of these if I've done my job right. Now you'll notice the first chunk of these guys are all in these little brackets, right? Do not worry about them. Do not worry about them. They are just little messages this computer sends to other computers so that it knows what's going on. We're not going to use them. We want to look at this table, which by the way is called an beautiful timing on stopping there, Mr. Fay. An ASCII table. And these are still used, by the way. This is only a half an ASCII table. We're going to look for our capital H. So I'm going to zoom in. Where is my capital H? Oh, it is number 72. And I write that. Do not worry about the hex for now. My capital H is written 0100 1000. Cool. So my first character, right, of my message, hi class, would be, let's see how good Mr. Fay's memory is. Probably not that good. 0100 1000. 0100 1000. So you need to fill this sheet out with a message, this sheet here. Then you're going to hand it to your friend and they're going to decode it using their ASCII table. So once again, just write your message on a little piece of scrap paper. Don't write it on the back of this sheet here. If you write it on the back of that sheet there, it's going to be a problem. Don't show your friend first. If you've got an odd number, write a letter to the teacher. Fill that out with binary. Your mate decodes it. Okay? I would like the teacher, if they could, to keep these so that I can take a look and see who's worth a lolly and who's just been mucking around for the whole session. Beautiful people, that is kind of the end of my talky bit of the lesson. Just a few reminders. A bit is the smallest information you can have. A byte is 8 bits. Those terms actually came before computers. And a computer uses bits by trying to sense whether or not there is electricity going down a pipe. It's 1 because there's electricity there. Thank you for being so patient. You've been a wonderful audience, and I look forward to reading your messages. Have a lovely day.